All right. How you guys doing? Doing okay? I'm probably a little more than halfway done grading the exams, so plan to have those back for you Thursday. I haven't decided on a particular time that I'll host the exam recap Friday, but that's still part of the plans. I'll make some announcement. If you guys had some particular time you'd really like to have it, feel free to let me know. At the moment, I'm kind of flexible. So we'll go over the exams Friday. I'll pass them back Thursday is the plan. And right now, today we're going to go through, we're going to come back and talk about biological oxygen demand. So within the context of wastewater, we talked about this as kind of the primary conventional pollutant that we target because we don't want our rivers and waterways becoming anoxic because all the bacteria demand all the oxygen, right? We want to leave some oxygen for the fish. So we're going to come back and talk a little deeper about that with the plan of understanding how do we put some math to it? How do we know how much BOD is in the water? How do we do a test for that? And then further, we can go on and say, well, what if we do discharge some BOD? How much does that affect a river or stream? And where will it be a problem? Because if we discharge some substance that bacteria can use to grow, they're not going to demand the oxygen like in that instant. It's not going to be a problem right there, right where the wastewater plant discharges. It's actually going to be somewhere further down the stream where the effect really becomes the most severe. So how do we predict that? How do we model that? How do we figure out where exactly the problem shows up? So in the next lecture on Thursday, we're going to get deeper into modeling it as a function of distance or time downstream. Today, we're going to go back to kind of the basics of what is BOD, how do we describe it, and how do we count it? How do we find out how much is there in a lab? So, as we talked about, it's essentially microbe food, right? BOD, this biological oxygen demand, or its oxygen demanding substances might be a better way to describe it. It's essentially the amount of biodegradable stuff. So what we are going to quantify is the amount of oxygen demanded according to allowing bacteria to eat this stuff. And that's going to happen typically over the course of 5 days. So we're going to have this oxygen demanded over some number of days. 5 is the typical. You could, of course, use 3 days or 7 days or something like that. But 5 is a good number because it kind of scopes out the majority of the biological oxygen demand that will occur will happen within the first 5 days. And so after that, you're not getting a ton, and it already takes a while to wait 5 days before you get your result anyway. So it's kind of not great to wait too many days, but you have to wait a few days for the microbes to do their thing. So they're going to consume this oxygen, create some cells, and release some CO2. That's kind of our overall equation. So we can describe BOD then as a subset of the theoretical amount that some chemical compounds could exert if you converted it all to CO2. So a bigger picture, we could talk about the theoretical oxygen demand. So if we add sugar, for example, glucose, C6H12O6, we could use our stoichiometry to say, okay, well, how many oxygens do we need to add to get this to go completely to CO2 and water? And of course, we'd have coefficients there and there. So this would be the maximum possible, and this is if we give it ideal oxidation environment so that this happens completely. That would be the theoretical. The biological oxygen demand will be less than the theoretical, by definition. It has to be because some of the carbon are going into cells, for example. And building cells doesn't necessarily demand the oxygen that going to CO2 would require. So If theoretical is if we had total information about all of the molecules that are in our waste, which we never do, then we could count exactly how much it would take to do pure oxidation. So BOD then is a subset of the theoretical, and we could also look at an oxygen demand, which is similar to the theoretical, but this is also an experimental version. And in the experimental version, not every single carbon atom will get converted to CO2. There will be some scenarios where it's rather resistant. If you take the perfluorinated carbons, for example, we use them in fire retardants often because they resist that type of oxidation. So if you have some molecules like that, or with some nature that is similar, maybe they'll resist oxidation under the conditions we give it. And so they will not consume oxygen. They will not be counted in a chemical test to see if we put in certain chemicals. Now this will overestimate the real BOD, but sometimes it's quite useful. Sometimes we use it to test to see if, let's say, our landfill is leaking, the leachate collection system perhaps has a problem. We can find pretty easily whether or not there's landfill effluent, landfill discharge, contaminating some water by checking this parameter. And you just send it to a lab, run it, takes 20 minutes or something, you oxidize, and you learn your result that same day instead of 5 days later. So this type of thing is used with some frequency in some fields. We generally don't use it for the wastewater field because we will continuously do these BOD tests, and that's a better estimation of the biological stuff that we really are concerning ourselves about. But I wanted to mention it. It's essentially taking some strong oxidizing conditions, maybe it's hydrogen peroxide and UV, maybe it's temperature and perchlorate, something highly oxidizing, and blasting it. And it's going to convert things like the organic matter, maybe some things like ammonia. You're adding enough oxygen, and you're taking that stuff to CO2, in this case, for the ammonia case, to nitrogen, things like that. So just as examples here, these are none of these are like specific exact balanced equations. I'm just showing you the direction that these molecules will tend if we're sending them through a process like this. Okay, in both of these cases, we also get some stable byproducts. So I mentioned the ammonia could go all the way to nitrogen, could also be nitrate, nitrite. The phosphorus within our organic molecules could get to phosphate. So there are some other stable intermediates that we might be concerning ourselves. And what you'll notice is many of these have oxygen in them, right? And so that's oxygen coming from the environment, coming from the dissolved oxygen in the water, being added to these molecules. So that's part of the demand. And it's a conversion that's occurring. So we can notice we can find that O demand, the oxygen demand, to make these. Okay. So we can take a look at the overall biological oxygen demand or biochemical oxygen demand, and we can classify that into some subcategories as well. We're not going to go too deep into this. I'm just introducing this concept for you. There are more things than just carbon-containing molecules that can exert this demand. Just like we saw a moment ago, where, let's say, NH3 can go to NO2 minus, that's nitrite, and ultimately to nitrate. What we're doing here is we're taking oxygen from the environment, but you see there's no carbon in this molecule, so this is nitrogenous biochemical oxygen demand. Normally, in the context of wastewater, we are often using the carbonaceous or just them both together as a total. But if you really got down into the weeds, you could take a look and say, oh, okay, well, this is the amount coming from nitrogen sources, this is the amount coming from other sources. And it could be not just ammonia, it could be some amine group on a bigger molecule that is processed, the microbes chew it up and spit out nitrate. Okay, that could be part of it, and in fact, some cells get energy doing this type of thing. If we had a situation where the chemistry was right for it, they're going to be doing that stuff. So this would get us to the nitrogen cycle, and I just want to highlight a couple things in the kind of more global nitrogen cycle for you. We have almost everything we breathe, about 78% of it is nitrogen gas, N2. It's very stable, very inert, meaning it doesn't react much with anything. So it's very hard to take that and make it into something useful for life, but it's everywhere. There are some microbes that can do it, and we've found some industrial processes that can do it to make fertilizer, the Haber-Bosch process. And so we have nitrogen-fixing bacteria that will take it from N2 into some organic form of nitrogen. They'll make cells out of it. Microbes in the roots of legumes, like peanuts, for example, are really good at this. So you can fix some nitrogen, and they're essentially fertilizing themselves in some sense. And then ultimately that's creating some organic or ammonia version of it. And so you get organic material that could then decompose, and then you can get ammonia from the ammonification process here, NH3 or NH4 plus, ammonium. From there, then the oxygen demand could happen, and you would get nitrites, nitrates, and then we have some bacteria that'll take those back up to N2 gas. Those are also not, you have to give them the correct form, but they'll take this from NO3 minus and send it out into the atmosphere as N2. Plants partake in this, microbes partake in this, animals that eat these things partake in this and then decompose and all of that, right? So this is just a kind of a quick rundown of the nitrogen cycle, and in our wastewater treatment plants, we are often aiming to accomplish one or the other of these aspects, or at least needing to understand where the nitrogen is going, because when we discharge it, we want to make sure that A, there's not a whole bunch of oxygen demand because of all the ammonia, plus ammonia is toxic, so we don't want too much ammonia anyway, and we want to make sure we're not flooding our rivers and waterways with excess nitrogen that bacteria could use or other organisms like algae could use, could cause some other problems. I think we'll have time to talk about that a little more when we come back from Thanksgiving. So we are often a little bit concerned about it. Wanted to just highlight this. Those of you who have had some environmental courses probably familiar with it, and if not, in either way, don't worry too much about it. I'm just highlighting this is an important process, even if we normally focus on just the generic oxygen demand that's usually carbon-based. Okay, so how do we measure this BOD stuff? Well, we need to take special care because it's easy to lose our oxygen to the atmosphere, or rather gain oxygen from the atmosphere into whatever container that we're trying to do our careful measurement in. If we want to count how much oxygen is used, what we have to do is seal it off from the atmosphere so that no extra oxygen can come in. So we need an airtight bottle, and it's very common to use 300 milliliter bottles, so a third of the size of this, approximately, and to have it sealed nicely, and we see these oxygen sensor caps here. So you'll see in environmental labs pretty often, these just little oxygen sensors that also act as a gas-tight seal to cap the bottle and say, okay, no oxygen can come in here from the atmosphere, and we can measure at the same time how much oxygen is in the bottle. So that's really important because we want to know how much is going away. So with that, we also want to make sure that no oxygen can be created inside the bottle. And that's actually kind of a valid concern because we know photosynthesis can convert CO2 to oxygen. So it's not like we're creating oxygen atoms out of nothing. We're not playing God here. We're just worried that our CO2 that the bacteria are producing for the BOD could be reconverted back into oxygen if we have photosynthesis. So we want to make sure to make it essentially dark. And the amber colored vials here usually is pretty good, is good enough, blocks out all the light that could be used for photosynthesis. So you'll see either bottles wrapped with like aluminum foil or amber bottles. Excuse me. And then we set it up and allow the biological activity, whatever's going to happen, avoiding photosynthesis, we allow that to happen for 5 days under those conditions. Now, if we have a whole bunch of waste in our water, there's going to be a big number here, a lot of oxygen demand, and there's actually not a lot of oxygen that can dissolve into water. So at best, the absolutely ideal conditions, we can get something like 15 milligrams per liter, maybe 16, of oxygen in water. Normally, for example, in this water, it's more like 8 to 10 range. Room temperature, oxygen dissolves better into water at cold temperatures. We're not going to use cold temperatures because we need the biological activity, and that's maybe we would match the river or something we're studying, but typically we'll use something more like room temperature. So our waste, therefore, is almost always too strong because it'll get rid of all the oxygen and our measurement goes nowhere. It says we removed it all, but we could have removed more and we just don't know how much more. So we might be able to measure, oh, the BOD is at least 8 milligrams per liter, but it might be 80, it might be 200. I don't know how much more than 8 it is. And so then we have to dilute our waste. We'll account for that with some calculations. We'll see that's not a huge deal, but it does add a little complexity to our math here. So we'll say typical dissolved oxygen max is something like 10 milligrams per liter. Okay, and we had a question. Thank you for that. So the bacteria consumed a bunch of oxygen in the process of breaking down the organic waste. Yes, that is exactly what we're tracking, is how much oxygen the bacteria are taking from the water while they're breaking down that waste. So that is exactly our BOD. By the way, the 5, you'll often see this subscript. That's the 5 days. So BOD 5 is our standard, and this is going to be milligrams of oxygen per liter. And this should be oxygen demanded if we really get specific. We'll say typical wastewater BOD ranges from something like 60 to, I think we said something like 400 or 500 milligrams BOD per liter. All right, so another question. So that is directly related to how much waste is present, right? Yes. And then the question goes on, the less waste that is there, the less oxygen the microbes use. Correct. So if the microbes don't have much food, they're not going to do much respiration, and therefore they're not going to consume much oxygen and produce much CO2. Theoretically, we might be able to track CO2 and watch that change. There's a few reasons we wouldn't want to do that, in part because it's the oxygen we really care about. Some of the carbon might go into cells, but also consume oxygen. But that same idea is there. The more food, the more oxygen is taken. Okay, so how do we calculate what's in the bottle? And how do we find the BOD measurement? So let's consider a bottle, this 300 milliliter bottle. We're going to usually make it completely airtight, but just for the sake of showing there's liquid in here, I'm going to put a little line there. We have DO, meaning dissolved oxygen. Initial, we'll have some value for that. This will be the same as any water that's at saturation, at equilibrium with the atmosphere. However much can enter there from natural processes is going to enter there. That's going to be that 8 to 10 range. So we can find that, measure that, or be given that. So our BOD 5 will be equal to that number minus the final number that we have, and we'll divide that by whatever dilution factor we had to use. So P being a dilution factor, and that would be some volume of wastewater divided by the total volume. So this would be V wastewater divided by V total. Would be another way to describe that, where we have probably a little bit of wastewater and a lot of dilution water. Okay, that's going to be typical. Again, thinking about how much oxygen we have to work with, it's not a lot, and how much waste, the strength of the waste, which is usually a lot. Okay, so with this, we can take what we started with minus what we ended with, divide it by that dilution factor, and we'll get our answer. Pretty straightforward. And usually we will do these calculations in milliliters for the volumes. And what you'll notice is the P here, this is a ratio. What portion of the volume is wastewater? And because it is a portion, the milliliters cancel, and we don't have to do any conversions to worry about the milligrams per liter versus the milliliters that we're doing the volumes with. So this is the portion of the bottle, we'll say, that is wastewater. Okay, so that means if we do a 1:20 ratio, maybe we have, not doing the math in my mind very well here, but 15 milliliters of wastewater and the rest up to 300 total milliliters of dilution water, 275 or 285, if I did that right. That would tell us, okay, what portion of this, the 15 divided by 300 would tell us how much, and that should be 120 if I did that math right. Okay, so let's do an example. Here, what we're doing so far is rather simple. What we'll find is on Thursday, what we'll do is start making use of the more mass balance, the reaction rates, and a river will act like a plug flow reactor. So we'll actually be able to connect several dots here and consider what really happens after we treat our wastewater. Okay, but for the moment, a very simple problem here. Let's take a 10 milliliter sample of sewage mixed with enough water to fill a 300 milliliter bottle. It has an initial DO of 9 milligrams per liter. And to help assure an accurate test, we want to have, or it is desirable to have, at least 2 milligrams per liter drop. Our DO sensors might not be perfectly accurate, so we want to make sure it drops a little bit, or like more than just a tiny bit. So at least 2 milliliters down, milligrams per liter, over the 5 days. And we also want to make sure we have at least 2 milligrams per liter of oxygen remaining to make sure, again, that our oxygen meter is working well in that range. So then the question is, for what range of BOD5 would this dilution produce the desired results? So I'll give you a few minutes on this. You should be able to do it. I'm going to remind you of the two equations we just looked at. And of course, feel free to work together, ask questions, figure out what the question really is asking and how to approach it. All right, so take 5 minutes on that. Making some sense of it? Got it? Okay. So let's take a look. I kind of sketched it out a little bit. First of all, we could take a look at the p-value. We had 10 milliliters of wastewater in 300 total. So that's going to be 10 divided by 290 plus 10, 10 divided by 300, or 1 over 30. Okay, so then to get the lowest amount of BOD that our setup can reasonably get, we have to think about what the question was asking. We wanted at least some minimum drop. That condition should correspond to our low case, because the smaller the drop in oxygen, the smaller the amount of wastewater in the system. On the other side, we had some maximum drop that we could find where the final was down to 2 milligrams per liter, and we didn't want to go lower than that, so that would be our maximum. So the highest case, in both cases, we know it's 9 as a starting point, 9 milligrams per liter of oxygen. The highest was going to be down to 2, and the lowest was at least a 2 drop, which means the drop itself was 2, and the DO final should be 7. And what I'll say is, so this would be a 2 milligram per liter drop, and here would be a 7 milligram per liter drop. Then we need to account for the dilution factor to find the BOD. So BOD would be 2 divided by 1 over 30, or just 2 times 30 would be 60 milligrams per liter of BOD. And in this case, 7 times 30 gives us 210 milligrams BOD per liter. So we could say the range should be 60 to 210 milligrams BOD per liter. Okay, makes sense? So this is a simple problem just to exercise, okay, what is this talking about? What is the drop? What are each of these pieces meaning? DOI is the DO initial dissolved oxygen, DOF, the final, and so on. Now we have a complicating factor. When we dilute the water, we actually have a risk of diluting it so much that there's not really enough bacteria to do the job. So if we dilute it with a bunch of pure water, which is, ideally we'd use pure water so that we don't complicate things. If we do that, we may have inhibited our bacteria so 5 days is no longer enough. We'd have to let them grow up, and everything takes longer and it's not so reliable. So we have to seed the dilution water with some extra bacteria, and bacteria don't like hanging out in pure water. They need some sort of media to grow in and to be happy in, especially if we want them to be able to adapt and start growing and being happy in some new environment. So we actually have to add a little bit of BOD with our bacteria, complicating things. It's not a lot, but it's enough that we have to account for it. So when we make a seeded dilution, we have a little more to account for. So this seed that's added to VD will have its own biological oxygen demand. Now it's going to be low enough that overall we are still diluting the wastewater. And overall, on the whole, we can count our BOD according to a very simple mass balance, right? The BOD of the mixture, when we do the seed plus the wastewater, is going to be the BOD of the wastewater times its volume that we added, plus the BOD of the dilution water times the volume of it that we added, right? Very simple, very straightforward. We're adding two solutions together, and we're doing conservation of mass on BOD. So that much should be pretty simple and straightforward. And we're going to go from there to figure out how we can find from two experiments, one with the mixed water and a separate one with just the dilution water, because we need to test it every time. How can we combine those two pieces of data to find, essentially rearrange this equation and solve for the BOD of the wastewater, which is what we're really interested in. This is always what we are aiming for from an operational standpoint. So that's what we are going to tackle. Now, one thing we can do as we rearrange this problem is get several things in terms of the dilution factor P, or in some cases 1 minus P. So if we think about it, P is the ratio that is wastewater. So what portion of the total water is wastewater? We could take the portion that is not wastewater, is the portion that is the dilution water. And that would be 1 minus P. So this would be VD divided by V total, or VM, right? This would be V wastewater plus VD. Okay, so if P is the portion that is wastewater, 1 minus P is the portion that is the dilution water. Okay, so then we can, each time we see a BOD term, on the right side of this equation, we have a bottle that's going to do that experiment for us. Or excuse me, I said that wrong. The mixture, we're doing an experiment, and the dilution water, we have a second experiment. I'll elaborate on that in a moment. So in these two conditions, we have a bottle that we're testing. And I'm going to highlight that in a different color to make that very clear. We'll call it bottle 1 for the moment. And we will also say this guy is being tested, or we are testing it in a second bottle. Yeah, and I apologize. I have VM here. Earlier I was saying V total. Those would be the same thing. So V total is V of the mixture. Okay. So if we look at that equation, we're getting data for it in two different places, two different bottles. That will allow us to figure out that third unknown. We experimentally get two of the unknowns so that we can find the third. Okay, so this will all rearrange nicely so that we can just straight up solve for the BOD of the wastewater given the results of these two experiments. That's where we're heading. The derivation looks like this, where we say we want to find the BOD of the wastewater. We're going to rearrange, and we can get there by dividing everything by the volume of the wastewater. When we do that, we will see a few things drop out. First of all, this will go away. Then we end up with VD over V wastewater, right here. And we will end up with BOD mixture times VM over the V wastewater. That's going to show up right here. We've also moved the BOD of the wastewater to the left, subtract it from both sides, and we're just flipping the sides here. So we're just putting BOD of the wastewater by itself, subtracting this guy from both sides, and we get this. BOD of the wastewater equals BOD of the mixture times VM over VWW, the wastewater. All that minus BOD of the dilution water times VD over V wastewater. Now, from here, we can convert it into P's instead of the VD, VW stuff. So just recognize that V wastewater over V of the mixture is P. So the V mixture over the V wastewater is 1 over P. So this guy becomes 1 over P. And then on the side over here, it's a little bit, not quite as clear, but if you do the math, this will work out such that VD over V wastewater can also be described in the form of P. That would be 1 minus P over P. Okay? So that would be, that will simplify accordingly. All right, that gives us, at the end of the day, an equation where we have a P in the denominator in both cases, which is partly why we bothered to get it into this form in the first place. So we'll be left with an equation that is the BOD of the wastewater is equal to the BOD of the mixture minus the BOD of the dilution water times the portion that is dilution water. So that's times 1 minus P. All of that over the dilution factor. And this equation you will have on your formula sheet. Okay, does that make sense? Following that? All right, so then when we perform these two experiments, to get the information, what we're going to do is take this guy and put DO initial and final measurements for each bottle. And that means we need probably 2 separate terms for initial and final. And we're going to call those DO initial and final for the mixture experiment, and BI and BF for the dilution experiment. So if you recall, this was BOD of the wastewater minus BOD, not the wastewater, the mixture, minus the dilution times 1 minus P, all of that over P. So what we're doing here is we're just saying here's our mixture on this side, and here's our dilution water only. So when we check to see the BOD of the dilution water only, we fill this with 300 milliliters of completely dilution water. Whereas in this one, we have some amount of wastewater and some amount of dilution water. And the V mixture of the two is equal to 300 typically 300 milliliters. I'm not planning to change that number, but theoretically you could put it in 200 milliliters or something. Okay, so then the initial dissolved oxygen is DOI in this bottle, and final is DOF for this bottle. And here, the initial is BI, and the final is BF for this bottle. B is just what the book uses, and that's why I'm using it, okay? And the equation you'll get on the exam might actually be this one. I don't remember. But what you can see here is if we take initial and final measurements into two different bottles, and we know how much we diluted the mixture bottle, we have all the pieces we need, right? Just a matter of piecing things together and understanding what goes where. Okay, so give it a try. Here's another problem. We have a test bottle containing just seeded dilution water. Its DO level drops by 1 milligram per liter in a 5-day test. And we have a 300 milliliter bottle filled with 15 milliliters of wastewater, and the rest is this seeded dilution water. Sometimes this would be expressed as a dilution of 1 to 20. And that one experiences a drop of 7.2 milligrams per liter in the same time period. The question is, what would be the 5-day BOD of the waste? So take 5 minutes and work on that. Should be able to do this given what we just talked about. All right, so one of the things that could trip you up here is if you weren't connecting the language of the problem itself when it was describing that something in the bottle dropped, some DO drop. When I was giving you DOI minus DOF, you have to interpret there that what we described in coming up with the equation in the first place was a drop in dissolved oxygen. That's what we're physically observing. So we have some initial measurement and some final measurement, and we have some drop in between those two time points, and that's what we are really concerning ourselves with, and that is the DO drop. So in the mixture case, that's DOI minus DO final, or it could be in the dilution case, BI minus B final. So those are where we would get the numbers, and we could put in then 7.2 minus 1 times 1 minus 0.95, all that divided by 0.05. So this should come out to be, so 7.2 minus, this will be 0.95 times 1 is 0.95. So that should be 6.25, is that right? 6.25, and then we can multiply that by 20. We take the 1 over 20 up to the top. Was that 100, 125? What is that? Or did I do that right? 125? Okay, does that make sense? Any issues? The B? Yeah, there's not really a good rhyme or reason why we're labeling the dilution water as B. That's just the way it is. To be or not to be, it is B. I guess D was already taken, so there you have it. Okay, does that make sense? Any issues? Right, so it's pretty straightforward, but there's a few pieces where you could get backwards. So worth studying DO versus B and all that. So we have a little bit of time left. I want to start talking about really what happens after we discharge some dissolved oxygen. This is the type of stuff that we will develop our plug flow reactor models for, and we'll get into more of that on Thursday. So if we discharge some BOD, or we even just put it in a bottle and watch what happens, we could track how much oxygen-demanding substance is remaining. And on the flip side, we could also track the oxygen in the water. So we're going to start on this slide with BOD. And the reason it's pretty interesting to look at a river is because it's going to act like a batch in many cases, right? Because you'll have some flow, maybe we can assume it's relatively constant, so we can have a distance or a time downstream. And it's going to act close enough like a plug flow reactor that we can treat it that way. So we could look at dissolved oxygen, of course, and then we can add in a new term called oxygen deficit and track that over time. So first of all, let's consider what happens to BOD. We add it to the river, our waste stream. Hopefully it's decently treated, but it's usually going to be at least somewhat elevated. Well, initially, we have some starting amount. And let's draw that right here. So this would be kind of an initial BOD. Well, over time, we expect oxygen to be mixing with the water, microbes to be eating it, and so we expect that to be diminishing over time. And the easiest to eat stuff will be eaten first. And perhaps there's some some bit of mixing that has to occur before it accelerates. The bacteria around have to get acclimated to the new waste, something like that. So maybe it looks something like that. There's probably some natural BOD in the water, just from fish, wildlife, soil, organics discharged into the water, all of that. There's probably some innate biological oxygen demand. And so we're going to approach that, the natural level, over time. Now, if we then consider what happens to our dissolved oxygen over time, let me see, we'll come to that. Okay, so there's our kind of graphic. We expect BOD to be removed. It'll become something like a first order reaction, but there's more to it than that, as we will see. It depends a little bit on how much oxygen is available for the microbes. So there's going to be a few different reactions and things happening here that are relevant. Another way we can describe BOD, by the way, is TOC. You'll see this in our field, in the environmental field, a fair bit. TOC is just a term that describes total organic carbon. This should track pretty well as an estimate. It's actually, we measure it in a similar way where we measure the COD, the chemical oxygen demand. We see, okay, how much CO2 is produced if we oxidize the heck out of our solution. So that would be something similar, and this may be another way to estimate S. This is a similar measurement to COD. But this would only be capturing the carbon. Okay. So let's then consider what happens to our dissolved oxygen. Well, DO, we probably have some saturation value. So it's worth considering what is our saturation value. This will depend a little bit on the stream chemistry and a lot on the stream temperature. But again, this should be somewhere in the ballpark of 8 to 10 milligrams per liter. If we're down in the bayou, it's probably less than that. If we're up in a trout stream in some northern part of the country that's very cold, it's probably more like 14, something like that. We'll call it 8 to 10 for now. Well, when we add our waste to the river water, there's usually some natural deficit because there's some natural BOD in place. Or maybe we could start it right at the saturation. Sometimes maybe a problem will simplify it and just start right there. At any case, hopefully we've oxygenated our wastewater right before discharging so that we don't have an immediate disruption of the local ecology. And we are, since we have the ability to, I mean, we've got these blowers blowing air into our wastewater anyway, let's send a little bit into the stream right before it's discharged, right? Just before we send it down the pipe. So that is a common practice to re-up the oxygen concentration. So it shouldn't have an immediate impact, but as the BOD starts being degraded, we will start having some dip in our oxygen. And then what we'll see is the BOD is, kind of going away, if we look back on our plots earlier, and we have oxygen re-entering the water from natural aeration processes. So it turns out that if you take water, remove all the oxygen, and then you put it in the environment, open to the atmosphere, there will be equilibrium reactions bringing oxygen back into the water, and those happen better if you flow it faster, if you shake it around, if you put bubbles in it. All those processes will speed up our re-aeration. So what I'm drawing here is just a generic, guess type of a thing. But if you have a waterfall, it's re-aerating a lot faster than a slow-moving bayou, right? So there's different dynamics that will impact it here. But ultimately, we do expect oxygen to be coming back in and eventually taking us back up towards the saturation or towards the natural kind of steady state that we achieve. So then this would be our DO curve. And we could consider, if that's our dissolved oxygen, we could also look at what we call the oxygen deficit. So the OD, and again, tracking with the book here, this one does make some sense, but it's a lot of DOs and ODs, and don't OD on the DO. Okay? Our deficit then would be described as the difference between our saturation value and the current, whatever that happens to be, oxygen there. So that was the wrong way. This would be our OD at some time. And if we take a look at the overall picture here, we will recognize that at some point along this curve, we have some maximum deficit. And that gives us a tool to figure out, is it really a problem, or how bad is the problem, and where do we expect that problem to occur? So when we have right here some maximum oxygen deficit, we'll call it, we could trace that down to some specific time or spot. And as we'll see next time, we'll call this some critical time point. You guys have something to add or ask? What's that? Okay. All right. So this part is where we're interested, right? This is if this deficit is killing fish, that's what we care about, right? So whatever happens there, that's where we need to find it, and that's where we need to know how bad is it. Okay, so that's a big point of what we're doing next time with balancing our rates of reaeration versus rates of oxygen consumption, and we need to know all this about BOD, how it works, so that we can predict that. All right, does that make sense? So the deficit at any point along the way, we could potentially calculate for if we do our our mass balance on oxygen here. It's going to be a strange mass balance because it's actually this deficit that drives oxygen back into the water. So we'll describe that more next time, but the deficit here is essentially the driving force for reaeration. So the greater the deficit, the more oxygen we have coming in, which is really helpful, but that doesn't mean the deficit doesn't get so bad that we get a fish kill, right? So that's what we are trying to avoid. Okay, so we're going to do, I think we'll just do this last slide. I think we're going at a good pace, and we'll cover the remainder next time. So when we start taking a look at how quickly the BOD is removed, we're going to describe it with a term L. And this is going to give us the BOD remaining. And we're following the book here, so if you do get confused, you can ask me, you can also take a look at our book. But the LT would be the BOD remaining at some time t. The L naught, or the L initial, is the amount remaining at time 0, which should be all of the BOD that could possibly be removed. We would also call that the ultimate BOD. And here's where I'll remind you that when we do BOD 5, that's not all that could possibly ever be removed. That's just our best estimate, or a 5-day estimate. So we're getting into kind of strange waters here where we typically measure in 5 days, but this ultimate BOD would be, well, what happens if you gave it an infinite amount of time? So this would be if we measured until it just stopped changing at all, that would be that measurement, right? So the amount of BOD, if we measured until the oxygen stopped changing. So you'll see some problems that are described that way. Okay, so then when we want to do a mass balance and we want to track the rates of change of these things, we'll look at the rate of change of the remaining BOD as a function of time. We'll get some rate constant there. This will be a decay rate because bacteria are removing the BOD. And we can track that as a first order equation with respect to LT. And then we would get an equation. The remaining BOD would be equal to the ultimate BOD times e to the minus kT. So we've seen this before in other forms. The variable here is a little weird, but we can recognize that we can set it up this way. This L naught, the ultimate BOD, is essentially the BOD that was in the river plus now whatever was in the wastewater. So we can say, we can calculate that if we know something about BOD measured in the wastewater plus, excuse me. No, let me not confuse that. So I'll come back to this in just a second. So the point here was that the initial is just when we mix our two streams, we have a river flowing and then a discharge of wastewater that's added. Then we have some mixing zone, and once it's mixed, that's where we get our L naught. Okay, that's that point. Now, what we can recognize from this equation is that ultimately our BOD, or excuse me, our ultimate BOD is equal to the amount remaining after some time t plus the amount that has been demanded by that time t. So, for example, L naught would be equal to the amount remaining at 5 days plus the amount demanded over 5 days. Okay, this would be remaining at day 5 plus demanded over 5 days plus the BOD demanded over 5 days. Okay, does that make sense? All right, so this will be kind of the foundation. We will go on from here next time and start talking about, okay, how do we do reaeration? How do we track that? And ultimately bring these equations together to get a model of our oxygen downstream. Okay, so I plan to pass back your exams on Thursday, and we'll go over those with you on Friday virtually. I'll see you Thursday.